Good morning, my name is FAUZI, presenting on behalf of our group. Our project analyzes global energy data aligned with Sustainable Development Goal 7, which targets universal, affordable and clean energy for everyone by 2030. We cover 6 sections today: introduction, 4 statistical objectives, and our conclusion. Let us begin.
SDG 7 has one clear target: to ensure everyone on Earth has the access to affordable, reliable, and clean energy by 2030. The gap is significant. As of 2020, 753 million people still have no electricity, while 2.4 billion are still cooking with wood or charcoal, fuels that cause serious respiratory illness. This is not just an energy issue. It directly affects the health, education, and economic opportunity. To analyze this, we use the global data on sustainable energy dataset from KIGO, compiled by the International Energy Agency. The dataset covers 176 countries from 2000 to 2020 with 3,649 rows and 21 variables including electricity access, renewable energy share, clean fuel access, GDP per capita, and energy consumption. Our analysis addresses 4 statistical objectives: descriptive statistic, a t-test, correlation analysis, and a time series forecast, each giving us a different lens on the global energy situation.
Before conducting any analysis, the dataset was carefully cleaned and prepared to ensure reliable results. The datasets cover 176 countries across a 21 years period. Our unit of analysis is the country level average, where the mean value of each variable was calculated across all available years for every country. This produced one representative value per country and ensured consistency throughout all 4 research objectives. The 5 key data preparation steps were carried out. We began by removing 30 aggregates entries representing regions such as World, Africa, and OECD. Since these are not individual countries, they were excluded from our analysis. Next, country-level aggregates were generated using the SPSS aggregates function. Missing values were then addressed through list-wise deletion, meaning that each analysis included only countries with complete data for a variable being examined. We also assess outliers using box plot and interquartile range or IQR method. Countries such as Iceland, which has exceptionally high renewable energy share due to geothermal research, and Qatar, which records very high GDP per capita from their oil wealth, were identified as outliers. However, they were retained because they reflect genuine real-world conditions. Finally, for the independent sample t-test on Objective 2, we create grouping variables called econ group. Countries were classified as either developing or developed based on their median GDP per capita value of USD 4693, which served as the cutoff point.
Objective 1 is our descriptive analysis. The goal is to understand the basic characteristic of our energy variables before doing any hypothesis testing. We analyze 4 variables as country level average: electricity access, clean fuel access, renewable energy share, and GDP per capita. Starting with electricity access, the global mean is 78.59%, but the median is 97.65%. This large gap tells us that while most countries are near fully electrified, a group of countries with very low access pull the means down significantly. The skewness of negative 1.146 confirms this. The distribution has a long left tail. For clean fuel access, mean is 73 and 0.4%, and median is 82.59%. A similar pattern showing persistent reliance on harmful fuels in a subset of countries. Renewable energy share has a mean of 32.56% and median of 23.24%. with a positive skewness of 0.689. Most countries have moderate shares, but some with very high renewables use skew the average upward. GDP per capita has the most striking pattern. The skewness is 2.176, strongly right skew. The mean of USD 13,216 is nearly 3 times the median of USD 4,609. This confirms massive global wealth inequality, with a small number of very wealthy nations pulling the average upwards. This chart shows how three energy indicators changed globally over 21 years. The top line, electricity access, rose steadily from 73% in 2000 to 85% in 2020. That is a gain of 12 percentage points over 2 decades, meaningful progress. The middle line, clean fuel access, also improved from 58% to 68%, but the pace is slower, suggesting that cooking energy transition is harder to achieve than extending electricity grids. The bottom line, renewable energy share remained relatively flat, around 32 to 34% throughout most of this period. There is a sharp spike at 2020. This data artifact caused by limited country reporting for that year, not a real sudden change. The key message, electricity access is improving steadily, but renewable energy adoption has stayed stalled, which raised concern for the clean energy transition. These two charts shows how electricity access and renewable energy share are distributed across countries. The histogram on the left shows a bimodal distribution, two distinct peaks. A very large bar near 100% represents fully electrified nation. A smaller cluster at the low end, below 40%, represent countries with severe access deficit, primarily in sub-Saharan Africa and South Asia. This bimodal pattern is important. The global average of 78.59% hides a deeply divided world. Most countries have full access, while a concentrated group has very little. The box plot on the right shows renewable energy share. The median is at 23.24%. The box spans roughly 8% to 55%, and there are several outliers countries near 90 to 94%. This widespread confirms very large variability between nations.
Objective 2 move us into inferential statistics. Our research question is there a significant difference in renewable energy share between developed and developing countries? Our null hypothesis states there is no significant difference between the two groups. The alternative hypothesis states a significant difference exists. We test at the significance level of 0.05. As for classification, we use median GDP per capita of USD 4,693 as the cutoff. Countries at or above the median were classified as developed 82 countries, while those below as developing 81 countries. Before running the t-test, we verified three assumptions. First, the independence of t-test for each country is a separate analysis, and the result obtained was satisfied. Second, normality with over 30 countries per group. The central limit theorem supports approximate normality. Third, we tested homogeneity of variance using the z-test. The result was F equals 41.29 with P less than 0.01, meaning the two groups have significantly unequal variances. We therefore applied Welch t-test, which is designed for groups with unequal variance. The results are striking. Developed countries have a mean renewable energy share of 16.16%. Developing countries have 51.16%, a difference of 35 percentage points. The WELST statistic is negative 9.208, and the p-value is less than 0.001, which is well below our significance level of 0.05. Therefore, we reject the null hypothesis. The difference is statistically significant. However, interpretation is everything here. Why do developing countries have higher renewable share? You might expect the opposite. The explanation is traditional biomass. Many developing nations still rely heavily on wood, charcoal, and agricultural waste for cooking and heating. These are technically classified as renewable energy in international statistics, but they are not modern clean energy. They cause serious health and environmental problems. Developed nations, by contrast, rely on fossil fuels and nuclear power, neither of which count as renewable. So their lower renewable share reflects a different energy mix, not a worse environmental outcome. This finding has a critical policy implication, which is not judge energy progress by renewable share alone. We can conclude that the quality and modernity of energy sources matters far more than the headline percentage.
Our objective 3 investigate whether the GDP per capita is significantly associated with a country's share of renewable energy consumption. Our null hypothesis assumes that there is no relationship between these two variables, while our alternative hypothesis proposes that there is a significant correlation exists. To evaluate this relationship, we calculated two correlation coefficients. We use Pearson's R measure the strength of a linear relationship, and Spearman's rho, on the other hand, is a non-parametric rank-based measure and is particularly appropriate in this case because GDP per capita exhibits substantial positive skewness of 2.176. In other words, a small number of very wealthy countries could disproportionately influence a purely linear analysis. The results show a Pearson correlation of negative 0.398 and a Spearman correlation of negative 0.683. Both coefficients are statistically significant, with p-value below 0.01 based on a sample of 163 countries. Importantly, both coefficients are negative. This indicates that GDP per capita increase, the share of renewable energy consumption tends to decrease. Based on this finding, we reject our null hypothesis. The strong Spearman coefficient of negative 0.683 provides additional insight. It suggests that the inverse relationship is highly consistent across countries, even though it's not perfectly linear. This is expected given the presence of several extremely high-income economies that influence the overall distribution of GDP per capita. These two SPSS outputs provide a visual confirmation of the correlation result presented in Objective 3. The scatter plot on the left represents each country as an individual data point. The fitted regression line clearly slopes downward from left to right, illustrating the negative relationship between the two variables. As GDP per capita increasing along the x-axis, the share of renewable energy consumption generally declines along the y-axis. The regression output reports an R-squared value of 0.158. Taking the square roots give a correlation coefficient of 0.398, and because the relationship is negative, the corresponding Pearson correlation is negative 0.398, exactly matching the results obtained from our correlation analysis. The correlation matrix on the right extends to the analysis by showing the relationship among all 5 energy-related variables. A clear pattern emerges. Electricity access, clean fuel access, and GDP per capita are all strongly and positively correlated with one another. In practical terms, countries with greater economic wealth tend to achieve higher level of energy access across multiple dimensions. At the same time, renewable energy share show negative correlation with all of the other variables. This reinforces a consistent finding throughout Objective 2 and 3. Countries with higher income and broader energy access tend to rely less on renewable as a share of their total final energy consumption.
Objective 4. Time series model setup. Objective 4 moves into predictive analysis. The questions we are answering is straightforward. If global electricity has been rising since 2000, where does that trend take us by 2030? And is that destination good enough to meet SDG 7? Before running any forecast, we need to choose the right model. Looking at our data, 21 annual observations of global mean electricity excess from 2000 to 2020. Two things are immediately clear. First, the trend is consistently upward and roughly linear. There are no sudden jumps or seasonal patterns. Second, the series is relatively short, only 21 data points. These two characteristics point clearly towards Hall's linear exponential smoothing. This method is designed specifically for data with a stable linear trend and no seasonal components. It models two things simultaneously: the current level, where the data is right now, and the trend, how fast it is moving. Other models like ARIMA require a much longer series, and Hall Winters adds a seasonal component that simply does not exist in annual energy data. We split the 21 years into a training set and a test set. Years 2000 to 2016, 17 years were used to feed the model. Years 2017 to 2020, the final 4 years, were held back to test how well the model predicts values it has never seen. The two key parameters are shown on the right. Alpha, the level smoothing parameter, is 0.894. This high value means the model places strong weight on recent observations when updating the level. Beta, the trend parameter, is 0.000. The trend is fixed from the initial estimate and does not upload dynamically, which is appropriating given the stable linear pattern. How accurate is the model? The RMSE is 0.513 percentage points. The model was approximately half a percentage point away from the actual value during the test period. The MAP is 0.59%, well below the 5% threshold that defines excellent forecast accuracy. The model passes validation comfortably. Time series forecast results. With the model validated, let us look at what it actually predicts. The chart on the left shows three things. The solid dark line is the actual global mean electricity excess from 2000 to 2020, rising steadily from 73% to 85%. The orange dashed segment shows the model's prediction during the test period, 2017 to 2020. You can see this sit just below the actual values, which is exactly the conservative pattern we expect from a well-calibrated model. The blue dashed line extending to 2030 is the forecast. The bar chart on the right shows the residual during the test period. The differences between actual and predicted for each year. All four bars are positive, meaning the model slightly underestimated actual excess each year. The largest residual was 0.64 percentage points in 2020. These are small and confirm the model is reliable. The forecast table on the right shows project excess by year. In 2025, we expect 85 86.34%. By 2027, 86.39%. By 2029, 87.44%. And at 2030, the SDG 7 deadline, the model projects global mean electricity access to reach 87.97%. That number sounds high, but SDG 7 requires 100% universal access. At 87.97%, we are approximately 12 percentage points short of that target. In practical terms, even under this relatively optimistic forecast, hundreds of millions of people are still projected to be without electricity when 2030 arrives. The countries making up the remaining gap are concentrated in sub-Saharan Africa and South Asia, the same regions at the low end of our descriptive statistics. Closing that gap requires targeted, funded, and urgently delivered solution in those specific contexts, not just a continuation of the current global trend. Let me bring together findings from all four objectives. Objective 1. Descriptive statistics. Global mean electricity access is 78.59%, but the median of 97.65% reveals a bimodal world. Most countries are fully electrified while a concentrated group remains severely underserved. GDP per capita skewness of 2.176 confirms extreme global wealth inequality. Objective 2. T-test. Wealth's T equal negative 9.208, P less than 0.001. Developing countries have 51.16%. Renewable share versus 16.16% for developed countries. The difference is statistically significant, but driven by traditional biomass, not modern clean energy. Policy must focus on equality, not just renewable percentage. Objective 3. Correlation. Pearson R equals negative 0.398 and Spearman RHO equals negative 0.683, both P less than 0.001. Higher GDP is associated with lower renewable share. Energy development is closely tied to economic development level. Objective 4. Time series. Our model achieved a MAPE of just 0.59%. Excellent accuracy. The forecast of 87.97% by 2030 falls 12 percentage points short of universal access. Without urgent action, the SDG 7 target will not be met. Overall, progress is real, but structural inequalities are deep. Meeting SDG 7 by 2030 requires targeted investment, particularly in energy-deprived regions, and a focus on modern renewable energy rather than traditional biomass.